Hey there guys, Mr. Carlson here. Let's take a look at this situation that we've got right here. I've got a stick person at the top of a very tall cliff. We don't know how tall that cliff is, but we know that this stick person is having a lot of fun just throwing rocks straight down this cliff. So these rocks are not going in any horizontal direction. They're just being thrown straight vertically down. And for this, we're going to solve for a few things here. The first thing we want to figure out is, we'll say for part A here, we want to figure out how far does it go, or we'll say delta x, the distance that it goes, in the first 3 seconds. So what's the displacement of that rock in just 3 seconds after he throws it? And let's say the only information we know that the problem gives us is that when this stick person throws it, the rock has an initial velocity of 15 meters per second. That's how fast he's throwing it down. And that's it. That's all we know. That's all the problem gives us. We want to figure out how far it goes in 3 seconds. We know that it has an initial velocity of 15 meters per second. Now, when we're looking at problems like this, the one thing to keep in mind is that the moment that ball, or that rock, whatever it is he's throwing, the moment it leaves his hand, it becomes a free-falling object. And we've already learned that for any freely falling body, on Earth at least, the acceleration of it, the moment it leaves his hand, is going to be negative, we're going to say 10 instead of 9.8. We're just going to round it up to 10 meters per second squared. So we can make that assumption about this object as soon as it leaves his hand. The other thing I'm going to do actually in this case is I'm going to define that this direction here, so the downward direction, I'm going to, just for fun, to make it a little easier, I'm going to say that this is the positive direction. Normally we say that downwards is the negative direction, but in this case I want to make the math a little easier for me, so I'm going to make this the positive direction, which means that this acceleration now is going to be positive, and this is going to stay positive 15 meters per second. If we would have said that this is the negative direction, I would have to make sure that this acceleration is negative, and also I would have had to have made this initial velocity negative as well, since it's going in this direction. But I'm going to make it positive just to make it a little easier for us to solve. So jumping back over here, let's see if we can figure out how far the rock goes in 3 seconds. We're going to have to bring back some of our kinematic equations here, so I'm going to rewrite those up here. The first one, final velocity is equal to initial velocity plus the acceleration times time. Another one that we're probably going to need is displacement is equal to initial velocity times the time plus 1/2 times the acceleration times the time squared. And then one more that we may need, final velocity squared is equal to initial velocity squared plus 2 times acceleration times the displacement. So these should be pretty familiar to us at this point. We've used them quite a bit. So here's what we have to work with. We have one more, but I'm not going to write that out because we're most likely not going to need it. These are more the common 3 kinematic equations that we use more often than not. So let's see if we can get by with just using these 3. All right, we're looking for displacement, and we're given initial velocity, we're given acceleration, and we're given the time that it takes. So just looking at my equations that I've got right here, let's see, I can't use this equation here because I don't know the final velocity, which is going to be the same case for this equation right here. I don't know the final velocity, so I can't use this equation, I can't use this equation, but I can use this middle one because I'm solving for displacement. I have the initial velocity and I have the time. I also know the acceleration since it's a free-falling object. So we're going to use this equation right here. And it's already set up to solve for displacement, which is kind of nice. So delta x. And I'm just going to plug these numbers in as we go. So initial velocity, 15 meters per second. I'm also going to make sure that I write in the units for each one here because I want us to see how they're going to cancel out in the end. 15 meters per second times the time takes 3 seconds. 3 seconds plus 1/2 times the acceleration, which is positive 10 meters per second squared, times the time squared, 3 seconds squared. 3 seconds squared. Let me simplify this. So let's start with this. I've got 15 meters per second times 3 seconds. Now notice that seconds here is actually going to cancel out from this because seconds would be in the numerator for this, denominator here. And so those are going to cancel out when we multiply these two terms. 15 times 3 is going to give us 45, and it's just going to be meters that's left over for my units there. Plus, let's see, 1/2 times 10, so I'm just going to put that's going to be 5 meters per second squared times 3 seconds, and we're going to square that whole thing. So when I do that, it's going to be 9, and then we're going to square that seconds as well. So 9 seconds squared. And so you can see here, the reason I wrote that out is so we can see that seconds squared is going to cancel out when I multiply these two, right? So seconds squared goes away here. Seconds squared goes away here. And so notice we're left with meters on this term here, 45 meters, plus 45 meters, which makes sense because remember we're solving for a distance or a displacement, so it should be meters in the end. That's a good way to know that what we're doing is correct if our units end up canceling out to what we want in the end. And so 45 and 45, that means this rock is going to travel 90 meters in 3 seconds if we give it this initial velocity of 15 meters per second. Okay, let's try another part to this same question here, or this same scenario. Let's say we want to figure out how long it takes. I'm going to erase this, actually. Give us a little room here. So let's say part B. Let's say I want to figure out how long it takes the rock to reach, so the time to reach a speed or a velocity of 25 meters per second. How long is it going to take after I throw that rock with this initial speed? How long is it going to take before it reaches this velocity of 25 meters per second? All right. So in this case, I'm solving for time. I still have the same initial velocity, the same acceleration. This time I know a final velocity though. So let's come up here. I know final velocity. I know initial velocity. I know the acceleration. I just need to solve for time. And so therefore I'm going to use this equation right here. So I'm going to rearrange this though to solve for time since that's what we're interested in. And so if I'm going to rearrange that equation, well, let me rewrite it down here first. So initial velocity plus acceleration times time. So first I'm going to have to subtract initial velocity to get it over here on the other side. And then I'm also going to have to divide by acceleration to cancel it out. So our equation is going to become final velocity minus initial velocity divided by acceleration. And that's it. So let's plug in our numbers. Final velocity is 25 meters per second minus 15 meters per second divided by our acceleration is positive 10 meters per second squared. Crunch the numbers on that, and we're going to get 1 second is how long it's going to take, which makes sense because it's accelerating at 10 meters per second squared, meaning every second that goes by, it gains 10 meters per second of velocity. Well, if it starts at 15, 1 second later, it should be traveling 25 meters per second. So we really could have solved this in our heads without really having to think about it. But it's good to write out these equations just to see how they work in simple cases. And then once we get to more complicated ones, it should make a little more sense. All right, let's try another part to this scenario. So let me make a little more room again. Let's say for the third part, we want to figure out how long it takes, the time that it takes to fall a certain distance. So for part C here, let's say we want to know the time to go 170 meters. So a distance of 170 meters, how long is that going to take for that rock to go that far? Again, same initial velocity, same acceleration. Well, in this case, I know distance. I don't know the time, and I know initial velocity and acceleration. I don't know the final velocity. So again, like in that first part, I know I can't use this equation because I don't have the final velocity. And I know I can't use this one either because of that, because I don't have the final velocity. So it leaves me with this equation right here. The problem is, though, is notice that time is in two different spots in this equation. And that's what I'm trying to solve for. So let's write that out here. So delta x equal to initial velocity times time plus 1/2 at squared. And so you might be thinking to yourself, how am I going to rearrange this equation to solve for time in this case? How am I going to manipulate this equation in order to do that? Well, let's start plugging in some numbers first and see if we can figure it out from there. So I know my distance here is going to be 170 meters. My initial velocity is 15 meters per second. Time, I'm just going to leave as t because that's what I'm trying to solve, plus 1/2 at squared, so 1/2 times 10 meters per second squared was the acceleration, and then t squared. Okay, let's see here. So what I'm going to do is I'm going to bring this over to the other side here. So what we're going to end up with is 0 right here because there's going to be nothing. 15 meters per second t plus, I'm gonna also simplify this down to just 5 because 1/2 times 10 is going to give me 5 meters per second squared times t squared, and then minus 170 meters. And when we get in this form right here, and actually I'm going to switch these two terms around, and maybe you might start to see what we're getting at here. So 5 meters per second squared times t squared plus 15 meters per second times t minus 170. And maybe once we get it in this form, you might be able to recognize what we're getting at. This, when we get it in this form right here, what we have is ax squared plus bx minus c. And this, in case you haven't noticed yet, is going to be where we're going to need our quadratic formula. This is a quadratic. When I've got this form of ax squared bx minus c here, that's a quadratic formula. And so if you've forgotten, which I'm sure you have, what the quadratic formula is, so when we've got this form here, what we can use, I'm just going to write it over here. I think I've got enough room. X is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2 times a. And so here's my a, here's my b, and then here's my c term. I can plug those numbers into this quadratic formula to figure out what my x, or in other words, in this case, t, the time, is going to be what x is. That's our variable that we're trying to solve for. So really we can think of this as being t in this scenario. So I'm going to move this over a little bit. Actually, I'm going to go down a little further. That's what I'm going to do. So let's plug our numbers in to this quadratic and see if we can figure that out. So x equals, so negative b in this case. So here's my b term, 15. So negative 15. I'm just going to leave the units off in this case because those are probably going to take up a lot of space. So I'm just going to leave those units off for now. We're going to trust that the units work out in the end. So negative 15 plus or minus the square root. Let's see, b squared. So I'm just going to do that right away. So b squared, 15 squared is going to be 225. 225 minus 4 times a times c. So I'm just going to do that all right now, right off the bat. So it's going to be 4 times 5 times a negative 170. Since this is minus 170, I'm going to make sure I'm going to put a negative there for that 170. So 4 times 5 times negative 170, and that works out to be negative 3,400. So negative 3,400 over, and we've got 2 times a, so that's 2 times 5, so 10. And again, just leaving the units off for now, just to make it a little simpler for us. All right, let's simplify this a little more here. So looking at just this part right here, 225 plus 3,400, and we're going to take the square root of that. And so we're going to end up with negative 15 plus or minus 60.2. So that's 60.2 is this whole part right here, divided by 10. Okay, now remember that for when we're doing a quadratic here, this is plus or minus. So we're going to end up with two answers. The first answer being negative 15 plus 60.2 divided by 10. And then the second answer would be negative 15 minus 60.2 divided by 10. So let's do the first part first, where it's negative 15 plus. So we're going to end up with, let's see, negative 15 plus 60.2 divided by 10, and we're going to end up with 4.52 seconds. And then if we do the other one, negative 15 minus 60.2 divided by 10, and we're going to end up with negative 7.52 seconds. Remember seconds because that's what we're solving for here is t, the time, right? So I should have really put t here instead of x, t. That would have made a little more sense for me to do. So now which one do I pick? I've got two answers here. Well, since we're solving for time, time can never be negative. If my time value ends up being negative, that means we're going back in time, and that, at least as far as I know, is impossible. So we know that this has to be the correct answer here, that the time that it's going to take is 4.52 seconds. So for that problem, that's a little longer because in that case, we ended up having to use this quadratic formula. And so when we do this unit, make sure you keep your eyes open for that. Typically, it's going to be for when you have to solve for the time, though. So when you see a problem like that, you're going to have to end up using the quadratic formula to solve it. Okay, let's do, I know this is kind of a long problem. Let's do one more part to this. Make a little more room again. We'll leave the quadratic there, just in case. All right, last part, part D. Let's say we want to know how fast the rock is going after it falls a certain distance. So let's say it goes 75 meters, and we want to know how fast is it going after that, or the final velocity, basically. So we're looking at figuring out final velocity. All right, same thing. We know the initial velocity, we know the acceleration, we're solving for final velocity, and we know the distance. So I don't know the time in this case. So basically I don't know time, so that gets rid of this equation. It also gets rid of this equation because I don't know. I know the distance though, so I can use this equation here, which is already set up to solve for final velocity. So let's plug those numbers in. Final velocity squared. Let's see, we're looking at initial velocity squared, so 15 meters per second, and we're going to square that. So that's going to be 225. And then again, we're going to square these units. So meters squared over seconds squared is what that would be. And then let's see, we've got 2 times the acceleration, which is 10 meters per second squared. And then the distance was 75 meters. Let's simplify this. So we've got 2 times 10 times 75. Now notice meters in the numerator here, meters in the numerator here. So when I multiply these two terms, I'm going to end up with the same thing I got here, meters squared over seconds squared. So let me write that out, 225 meters squared over seconds squared. Plus, let's see, what do we end up with right here? 1,500. 1,500. And then again, it would be meters squared over seconds squared. Let's combine these. So we've got well, actually, we don't have to combine them. Let's just take a look at this. We know that this is final velocity squared, which means to get rid of that squared, I need to take the square root of that, which means I'm going to have to do it to both sides, which is a good thing because I've got this meter squared over second squared. And so when I take the square root, those are going to go away for that. So 225 plus 1,500, taking the square root, and we should get 41.5, and it's going to be meters per second. And that is our final answer for that one. Whew, that was a long one, but we made it.